Okay, we're going to have a conversation about pressure under static conditions. So static means that the fluid isn't moving, it's just still. Okay? So I've got a system here, a reservoir, a tank. It has a connection over to another tank, which is closed, except it does have a manometer attached to it. And at the top of the tank is a void space that's filled with air. Okay, so I've got liquid all through here. Under pressure, and then there's a void space here which also has some air that's going to be under some pressure. So I'd like to come up with a way to analyze how the pressure is changing in this system. So the first thing I'll do is write down a force balance in vertical, which if you look in your textbook, you can do a basic force balance and show that the gradient in pressure under static conditions is equal to minus rho g k, where k is a unit vector in the vertical. Okay, so it's helpful to write this out in terms of scalar equations. So instead of writing it as a gradient, we could write it as three different equations. The change in pressure with respect to z is equal to minus rho times g. The change in pressure with respect to x is equal to 0, and the change in pressure with respect to y is equal to 0. So this here, those three equations are saying the exact same thing as this equation. This is a scalar representation, this is a vector representation. Okay, so with that in mind, taking a look first at these two equations, what it means is that if you move in the x direction, there's no change in pressure. Or if you move in the y direction, there's no change in pressure. So if I'm here in the tank and I move horizontally, in the horizontal plane, I can move left, right. The pressure is not going to change. I'll have a constant pressure. This does not mean the pressure is 0. It just means that the change in pressure with movement in either the x or y direction is 0. So x is in this direction and y is in and out of the board. Okay, so these guys are our friends. That means that we can always move horizontally, and we can expect no change in pressure if we're within the same fluid. So I could go from here over to here along a horizontal line and the pressure will stay the same. Okay, so now if I look at this equation, this is where the action is. This is where we're saying that there's some change in pressure with height. Here it's saying that as you increase z, so increase in z is moving in this direction, I expect a decrease in pressure in proportion to the density and the gravitational constant. So going upwards in z means that pressure goes down linearly with z. Another way you can think about it is if you're going downwards, as you're going downwards, you're moving in the negative z direction, and in that case, you would expect a linear increase in z. Okay? So if I just define a coordinate here, we'll call this s, then I would expect, and I measure that from this point A, then I would expect that the pressure as a function of distance s is just equal to the pressure at A plus rho times g times this distance s. Okay? So pressure will increase linearly with s as we go down. And that means that down here at location B, the pressure at B is just equal to the pressure at A plus rho times g times this height, which is labeled h1. Okay, so that brings us down to B. So now I want to figure out what the pressure is here at C. Well, C is higher than B. What I'll do is I'll first slide over here horizontally to say location B prime. And since I know the change in pressure with respect to x is 0, I can move horizontally and there's going to be no change in pressure. So I know that the pressure at B prime is just the same as the pressure at B. And that's just equal to the pressure at A plus rho g times h1. So now as we go in this direction, we're going to reduce our pressure in proportion to distance according to that equation. So that means that the pressure at C is going to be the pressure at B prime minus rho times G times H2. So we see a pattern here. We see a pattern where as we go downwards, our pressures increase, and as we go upwards, our pressures decrease. So finally, I can write out that the pressure at C is just equal to the pressure at A, which is exposed to the atmosphere. So I'll just say P atmosphere plus rho times G times H1 minus rho times G times H2. Okay, so now I've analyzed the pressure at C, and I have this number, and then within this void space where the air is located, that will all take on the pressure at C. So all of this space here takes on basically the same as the pressure at C. So you have a problem where it says find the pressure in the void space. We don't consider the density of the gas when we worry about changes in pressure over short distances. We just worry about the liquid because the liquid's density is 1,000 times heavier than the gas density. Okay, the last question I have for you is this. I have a manometer attached to this tank. The question is, how high up this tube would you expect the water to rise? Do you expect the water to rise equal to this level, equal to the top, equal to here? Since this is a static system, wherever the interface is located will have an atmospheric pressure. And because of that atmospheric pressure, because if we go down, pressure increases, we go back up, pressure decreases. In order for the pressure to come back to atmospheric, the water level has to be right here, even with the other side. Okay, so a manometer, if it was attached to this tank, would rise up to this level. The water level here is not rising up as high because it's hitting this area that's filled with gas, and it starts compressing that, and we can't go up any higher because there's mass there. It's in the way. I hope this gives you a basic sense for how to work through some of these statics problems.